turn to page 29. Okay, so far we've talked about the fact that integral is the opposite procedure of derivatives, and we know derivatives is slope. If we undo that slope formula, we get x1 minus or x2 minus x1 times y2 minus y1. That reminds us of area. So we've been working with something that's area related these past 3 days. We started off with sigma notation to help us with the limit definition that we did on Friday, but we also used rectangles to approximate an area of a region. We did left-handed, we did right-handed, we did middle rectangles. We also learned about the new shape, trapezoids, on Friday, and how trapezoids can approximate a curved region even better than rectangles can, just because the way that trapezoids are shaped. Now, limit definition is kind of a long process, but it helps us see that we're adding infinite number of rectangles that can allow us to achieve the actual area of a region. Now, today we're going to start talking about power rule for integrals, and that's going to allow us to move through and find area a lot faster, a lot more efficiently than what we did on Friday. So after we learn this, we're going to leave that limit definition behind, but it's still going to be an AP topic, so we have to still revisit it. But and it'll be on your quiz on Friday. But we're not going to quite see how the power rule for integrals is going to help us find the area just yet. We're going to just learn about something called indefinite integrals, and then after the quiz, we'll really use the area feature a lot more. But okay. So if we remember power rule for derivatives, we're going to do a lot of similar things. Power rule for antiderivatives. So let's just review from first semester. If our function is x squared, okay, what will be your derivative? Will be f prime, 2x, right? And let's think about what we do to get to that 2x, right? So here's power rule, right? We bring the exponent down, and then we subtract 1 from the exponent, right? So that 2 from the exponent comes down, and we subtract 1. So if we think about putting the derivative power rule into words, we bring the exponent down in front of the variable, and then we, well, initially, when that 2 comes down, it does what with the x? Multiply, yeah. So if you think about what operation is we're doing there, and then we do what after that? Subtract 1. So imagine if we wanted to go back to where we came from, then instead of subtracting 1, we would do what if we want to go back to from add 1? Yep. So we're going to add 1 to the exponent and divide. Yep. So imagine you took 2x and you want to get back up to x squared, right? You would add 1 to the exponent. So initially there was 1, you add 1 to it, and then instead of multiplying, you're going to be dividing. So if I divide by 2, I get the 2's cancel out, and back to x squared. So that's basically what power rule for antiderivatives is. We were just undoing the process, and it should make sense to us that we're just basically working backwards. There are some notations that go along with it. Remember how with derivatives, we will see d over dx of x squared is equal to 2x. That just means we're going to find the derivative with respect to x. Now we're going to take the antiderivative with respect to x, and that is going to look like this form here. I know we're seeing u here, but this is these notations indicate that we're about to take the antiderivative with respect to whatever variable that we're dealing with. So before it was d over dx in the denominator, now it's going to be dx in the numerator. So if we want to do this 2x problem here, we would say the integral of 2x dx is equal to x squared plus c. Okay, I'll talk about what that c means, but I'm going to highlight the notation that is going to have to be shown in every problem. Really, when we do antiderivative, 2x becomes x squared, but the notation, the integral and dx notation, is just part of your integral process. Now, after you apply power rule, those notations go away, and then the plus c will show up at the end. So a couple of names for these notations. The integral notation is this kind of this F-looking symbol here. That just means I'm about to take the antiderivative. First semester, when we want to find the derivative, we would just do d over dx. But now the integral notation will indicate that we're taking the antiderivative. The 2x is called the integrand. This is the expression before the antiderivative is taken. This is the problem that we're working with. So. And then dx identifies the independent variable, just like how d over dx represents that I'm finding the derivative of x squared with respect to x. Here, that just means I'm taking the antiderivative of 2x with respect to x. So we don't do any calculations with that dx. It just goes away after we take the antiderivative. So the integral in dx disappears as soon as you apply power rule. And then the plus c is the constant of integration. Okay, that's going to have to show up each time we take the antiderivative. Okay, I'll talk about now what that plus c means and why we need it. So going back to first semester, let's say I had these three functions: x squared plus 5, x squared minus 13, x squared plus minus 126. Let me ask you this. What's the derivative of the first function? 2x. What's the derivative of the second function? 2x. Third function, also 2x. Now, these are all different graphs. These are all different functions. So why do they all have the same derivative? All the constant disappears. Okay. So let me ask you this. How many functions then share this derivative of 2x? How many in total? Like if you can.
Infinite?
Yeah, infinite. Why do you say infinite? Infinite numbers of constants, right? As long as it's in this x squared family, right? It's going to be x squared plus infinite numbers of constants. And that's what this plus c tells us. It tells us that, you know, how many functions share this derivative of 2x? As long as you're in this family of x squared plus infinite number of constants, they all share the same derivative of 2x. So that's why we need that plus c there, because we're basically creating a whole umbrella set of functions that all share the same derivative. Okay, so since we can add constants to any of these functions and still result in the same derivative, the antiderivative of a function will be in the form of f of x plus c to show the family of functions that all share the same derivative. Okay, the process of integration is called antidifferentiation, or taking the indefinite integral. Indefinite integral results in a function, like always see here. After the quiz, we're going to talk about definite integrals, and that's going to allow us to get a number out of this process, and that number will correspond with the area. So right now we're just getting to the area finding formula. We're not going to quite explore the area in terms of getting a number just yet. We're just learning the process, and this is what we're doing is we're finding the indefinite integral because there are no bounds involved yet. Okay, so once we involve bounds, then we can begin to create a area of a region that we're asking for, and that's where that definite is going to come in. Indefinite means you have the integral notation without a number associated above and below on that integral notation. Okay, so today we're just going to be looking to practice this process that we see here. where we're just going to add 1 to the exponent, divide it by the new exponent, and we're just going to do power rule. All right, so page 30. Now, remember, we had all these power rule conditions from first semester. How we use power rule more than any other derivative rule from first semester, but we have to also keep in mind there are a lot of restrictions in place, right? We can't just do power rule whenever we want to. We have to sometimes do a little bit of cleanup before we can apply power rule. No, just in terms of cleaning up the expressions, right? We can't do power rule with variables in the denominator. You got to resolve all parentheses, all that. So those same properties, those same conditions will still apply with antiderivatives. So if you see a radical, you have to rewrite as a rational exponent, just like how derivatives work. If you see a variable in the denominator, you have to move a variable into the numerator. You cannot take the antiderivative. You can't do power rule, derivatives, or integrals if the variable is in the denominator. And then third, you want to expand your expression fully. If you see any parentheses, you got to get those parentheses out of the way. You got to expand, you got to FOIL. If you see parentheses that's impacting your expression, it's not going to get to your, you're not going to be able to get to your answer correctly. Okay, now the first few are going to pass all these conditions without having us to try it, but later on, we're going to have to do a little bit more work. Okay, so here, integral of 7x dx, this one, is this ready to go? Does it pass all 3 conditions? Yes, okay, so we're going to apply our power rule. Our power rule is here given by this notation here. That just means we're going to add 1 to the exponent, and whatever we get in that exponent, we're going to copy that exponent down, and that's my antiderivative. No, you got to memorize it. Yeah, okay. Yeah. Okay, so 7x dx. There's a hidden what? 1, right? So we'll be the power rule using antiderivatives. 7x 1 plus 1, 2. So 7x squared divided by 2. You're always, whatever new exponent you come up with, that's the same number that you're going to copy below. You're always going to, these numbers will always match. But do your exponent first, and then you can copy that number down. Plus what? C. We have infinite numbers of functions that all share the same derivative of 7x. You can leave it like this, or you can write it as 7/2 x squared plus c. Okay, 7x cubed dx. What's the antiderivative? 7x to the 4th over 4 plus c. What I see some students do, just kind of understand, kind of getting used to the notation. Some students would leave the integral and dx notation in the final answer. So just make sure we keep reminding ourselves the integral and dx is telling us we're about to take the antiderivative process, but once we do it, those notations go away. You're just left with an expression plus c. So don't carry the integral, that integral notation or the dx after you do the power rule. It disappears. Okay, number 3. What do you notice different with number 3? Yeah, we have 3 terms. Okay. Are there any issues with each of these 3 terms? Do they need any cleanup here? No, there's no parentheses either. There's nothing to expand. These are all standalone terms. So we can do power rule how many times here? 3 times. Okay. All right, so 2x becomes 3x squared becomes over 3, okay. Minus 5x to the 4th becomes plus, how many c's do we have? 3 c's, right? Now, let me ask you this. 3 times c is still a what? It's still a constant, right? So basically, we don't have to count the number of c's. We just can write it as plus c, because plus c is just any given number of constants. So we could just let that 3 absorb into plus c, and there's no need to add the number of c's based off the terms. Okay, any constants added together are still a constant. We just merge it into a plus c. It's not wrong if you do plus 3c, but typically we just say plus c and not have to worry about counting them. It's all just going to merge together anyways. Okay, some cleanup though. The 2s, 3s, and 5s can cancel out. That's right. You're always going to have a plus if 1c. Yeah. All right, number 4. What's different about number 4 now? Yeah, we have some things we have to worry about, right? We can't, just like how if you were to take the derivative of this expression, you got to do some cleanup first. Or I know we have chain rule, but here we have to expand it out fully. Okay. Okay. Careful though, we can't just distribute the 2 through. You got to write the parentheses out twice and take time to FOIL it out, right? So I haven't done any calculus to it yet. I'm just getting my expression ready so that I can apply power rule. Okay, there's one thing we haven't quite seen yet, but we'll get to that. 9x squared becomes
18x.
That's derivatives. Yeah, that's derivatives, right? Anti-derivatives. Well,
2x.
yeah, so we do 9x to the 3rd power over 3, okay, minus, okay, minus 6x squared over 2. Now, before we get to the next term here, let me ask you this. Whenever we do the antiderivative, what's happening to your degrees? Increase by what? By 1, increase by 1. So a degree 2 will go to a degree 3. A degree 1 will go to degree 2. Now the constant 1 is degree what? 0. So guess what the plus 1 will turn into? Good, plus x. Your tendency is you're going to want to make that 1 go to a 0 because you're thinking derivative, right? But this is antiderivative. So every constant, every degree is now going to rise, not going to fall away. So 2 becomes 3, 1 becomes 2, 0 becomes 1, and then plus c. Okay, so that's
something. It wouldn't be a c, it would be like an x.
What do you mean?
Oh, like so, like it raises from like a constant to like that.
That's right. That constant is now going to raise to a plus x. Yeah. If it was plus 4, 4 would become what? Or x. 5 will become 5x. Right. So that's something you got to kind of get used to because we're so comfortable with derivatives. We want to make constants go away, but antiderivatives is the opposite. Okay, do some cleanup here. So again, your notations at the beginning, your bookend notations go away. Just the plus c remains. Okay, number 5. What's an issue that you see with 5?
The denominator, and then it's also a rational.
Yeah, and a radical, right? We got to convert that radical to a rational. So my suggestion is if you ever see one term in the denominator, go ahead and split them up into individual fractions. Okay, I know some students may want to pull that root x to the top, but I think that there are some issues there. You have to make sure you put your x plus 1 in set of parentheses. I think it's just easier, just treat them like individual fractions, clean them up individually, and then go from there. Okay, so we have to do some cleanup here before we can even think about our calculus step, right? And also the root x can be rewritten as what? X to the 1/2, okay. Okay, so I like to separate because once you separate, then you're dealing with two smaller, easier problems rather than one messy one. Right? All right, how would the first term clean up to get it ready for power rule? What's my new expression after I do that cleanup? X to the 1/2, right? If I have variables above each other and they're the same, I can just subtract exponents, right? 1 minus 1/2 is just 1/2. What's the second term to get it ready for power rule? X to the negative 1/2. Now I have two individual terms that are completely independent of each other. I can just do power rule twice. Okay. All right, we haven't worked with fractions yet, so let's practice that. What does x to the 1/2 become?
X to 3/2. No, sorry.
You're right, x to the 3/2
Divided by
divided by 3/2. Okay, we'll clean that up in a second, but that's what we do, right? After we create our new exponent, just copy that number below in the denominator. Okay, what does x to the negative 1/2 become? X to the 1/2 over 1/2.
Would it make more sense? Would it make more sense to like make it like 1.5 and 0.5 or?
I would leave it like this. I mean, it's not wrong if you do that. You won't get points taken off, but I think it's easier. Just leave it as whatever they give you. Now, there is a complex fraction here. So how can I make it so that this doesn't look like a complex fraction? If I dividing by 3/2, the same thing as what? Multiply 2/3. So it just feels a little bit cleaner to resolve that fractional complex fraction. Dividing by 1/2 is the same thing as multiply by 2. Yeah.
I was gonna say.
You mean from here to here? Oh, sorry. Yeah, my bad. I dropped it without thinking about it. Okay, you're right. 2/3 x to 3/2. Thank you. All right. Any questions? All right, number 6. What do we need to do first?
We were to the right in the denominator is 1.5.
What would you do first? Yeah, multiplies the y's. This is y to the 1/2, right? So I have y times y to the 1/2. Let's merge them together so that we're not having to deal with two different y's. We can actually merge them together. What's y to the first power times y to the 1/2? Add exponents, right? If you multiply bases, you add exponents. Okay. Okay. So the y's are cleaned up, but it's still not quite in the right spot. So where does that have to be? Top. You got to bring that. Okay. So when it comes to the top, what does that look like? Yep. 3y to the negative 3. Okay. We're now ready for power rule. That 3 can just hang out in front. That 3 has no impact by our rule, but we're just working with power rule for that y to the negative 3/2. Okay, so 3 times y to the, what's the new exponent? -3/2 plus 2/2 divided by -1/2. Okay, let's do some cleanup here. Dividing by -1/2 is the same thing as multiplying by -2. And then to finalize our answer without negative exponents, what would your final answer look like? Yeah. So we bring down the y, but we don't bring anything else down, right? The -2 and 3 stays up top. Okay. I think we're ready for number 7. 7 is the messiest in terms of the cleanup. And we verbalize what we want to do before we actually do it. What would you? Yeah, you would expand that 1 minus x squared, FOIL that out first, and then convert your radicals to rational exponents, distribute, clean up all this mess, and then dividing by a fraction, we're going to split up into individual fractions, just like we did with number 5, which is that we're probably expecting more than 2 terms. And then once you individualize each fraction, then bring all the denominator variables up, get them all nice and clean, and then you can do power rule for each of them. Yeah. Yeah.
You have to separate that 3 times.
That's how I would do.
With the denominator.
That's right. I would do that. Yeah. Okay. All right. So as you guys go through the steps, I will also work through the problem the same time that you guys do. Okay. Let's see how we line up.
This was all 3 of the conditions.
I'm sorry?
This one was all 3 of the issues.
That's right. It does. Yeah. It has all the issues all combined into one problem. Yeah. So what is cube root of x? X to the what? Up there. Okay, so merging the fractions above and below, it's a little messier because you gotta find common denominators before you subtract, right? 1/2 minus 1/3, the same thing as 3/6 minus 2/6, which is 1/6. 3/2 minus 1/3 is the same thing as 9/6 minus 2/6, which is 7/6. And the 5/2 and 1/3 is 15/6 minus 2/6. Okay, so now everything is nice and ready. Now you can do power rule for each of the three terms. And then when you do power rule, now you can drop those notations that we kept all the way up to this point. It's a long process, but I mean, we know how to clean this up from a derivative standpoint from first semester. So we just clean it up the same way that we would if it was a derivative problem. The only thing is when we get to the stage, instead of going through your derivative step, you're gonna go through your antiderivative step, right? Instead of multiplying and subtracting, you're just adding and dividing. But everything up to this point should feel familiar. As messy as it is, we did this first semester, right? We cleaned up the exact same way if we were to get this ready for a derivative step, right? So that should feel familiar. Okay. Any questions here?
So what the implement the integration formulas like get to with this essentially?
What do you mean?
Like, you know, like the ones talked about at the beginning, like these three, the three at the top of the page.
Oh, the 3 is just power rule. This is just using a different variable here, but that's just power rule. This second one is just telling us that if I have a constant, my constant rises up to degree 1. And then the third one we haven't gotten to, this natural log rule, we're gonna get to next unit, so don't worry about this one. We've learned 1 and 2. Yeah, 2 is just basically just 1. We just have it a special case for the fact that a constant is not going to go away to 0. It's going to rise up to degree 1. Yes. Yeah, sorry. Yeah. Okay, well, are you good with this 7/6 being here? Okay, so after we find our new exponent, we divide it by the new exponent, which is the same thing. And then from here to here, I just did some cleanup. So dividing by 7/6 is the same thing as multiplying by 6/7. So 3 times 6/7 is 18/7. I didn't have to. That's just my preference is I like to think of that 3 as something that is separate. And I'm just going to do power rule with this so that it doesn't feel so messy. But it's up to you. You can have that 3 here if you want. But even if the 3x is 76 times 6/7, you're still getting 18/7. So either you leave the 3 with the x or leave it outside. We should still get the same thing. It's up to you if you want to put the 3 with the x. Our answers should still match. Okay, so you guys will have a practice with power rule today. I want to I want to start into the second part a little early so that we can maybe get through some things a little quicker and have some additional time for review. I mean, we're still gonna, hopefully I can start reviewing tomorrow and then review Wednesday, review Thursday, and then quiz. But there's one or two things that we have to kind of go over still. But this one should be quick. Okay, so if you guys can turn to page 31. Okay, 1 through 6, these should look familiar. These are trig derivative rules. Okay, and if integral rules is just undoing the derivative rules, then we should just be able to look at our derivative rules and just work backwards, and that should be our integral rules. Okay, so I want to just make sure that a lot of the rules that we learned first semester is going to apply because we're just going to read backwards with those rules. Let's review though our derivative trig rules so that I want to show you these 6 trig integral rules. We shouldn't have to memorize. We should be able to just read it off of what we know from derivatives. Okay, so I like to have it in 2 columns: sine, tangent, secant, first column, and then the c functions in the second column, right? All in alphabetical order. They all produce negative derivatives. These 2 look alike, these 2 look alike, these 2 look alike. Tangent and secant just involve each other. Cotangent, cosecant, derivatives just involve each other. Okay, so let's remind our rules here. Sine of u becomes what? Cosine of u times u prime. Now, when we go backwards, don't worry about the u prime. The u prime is kind of like the du, so just leave. Yeah, just want to come to that. Cosine's derivative. Tangent's derivative. Yeah, good. Cotangent feels a lot like all we did with tangent. Cotangent derivative is all right. Secant's derivative. Good. Yeah, it's just involve the one above it, right? These 2 are involved in the derivatives. Cosecant's derivative with a what in front? Negative. Okay. Okay, so these 6 derivative rules is still going to prove very useful this semester. I don't want us to memorize these trig integral rules. I just want us to be able to write these rules at the top of the page and just read them backwards because the backward is the integral rule. Okay, so if the derivative of sine is cosine, what do you think the antiderivative of cosine will be? Sine, right? If the sine produces cosine, then the integral of cosine will just bring us back to sine, right? Remember, these are all derivative level, and we're just trying to bring the derivative level up to the original function. So let's start here. So cosine just becomes sine of u plus c. I'm just reading this rule backwards.
What does the c stand for? Is it like in this case?
It's still saying that there are infinite number of trig functions that all share the same derivative as cosine. So plus c is still, +1 or +2 or +3. So plus c will always show up with any indefinite integral. Let me do the easy one first. I'm sorry about these stray marks. These should not look like they're negatives. These are all positives there on the right. Okay. Secant squared. What do you think the integral of secant squared is? Tangent, right? We know that tangent is secant squared, so the integral of secant squared will bring us up to tangent. What's the integral you think of secant u tangent u? The secant. Okay, the secant. Okay, cosecant squared. Yeah, so the negative has to go somewhere, right? If the integral of negative cosecant squared is a positive cotangent, then the integral of a positive cosecant squared must be a negative cotangent. All right, what do you think cosecant cotangent is? Negative cosecant u plus c. Okay, let's go back to the first one. What do you think the integral of sine will be? Negative cosine, right? You know the integral of negative sine is a positive cosine, so the integral of a positive sine must be a negative cosine. So these are pseudo new rules, but not really, right? If you know your derivative rules and you know how you're just working backwards, all these 6 rules are there in front of you. There's no need to memorize these. You already know these 6, just use these 6 to get to these other 6 rules. Now, having said that, these 2 give students the most trouble. So put a star next to these 2. Why do you think these give students so much trouble?
Exact opposite.
Yeah, because we're so used to thinking sine derivative is cosine and cosine derivative is negative sine, that when you get to the antiderivative, it kind of takes a minute to kind of let that sink in, right?
It's only the signs that flip this.
Right, I mean, the integral is still what we expect, but it's weird seeing the integral, seeing cosine associated with a positive sine. It's also weird seeing the sine associated with negative cosine, because we're so used to the signs and how they match. I think these 2 students don't have so much issue because they see the C function and they produce negatives, but these 2 are the ones that where students get mixed up with the sign. Okay, all right, check your calendar for homework. Come get your phone. Pleasure. Good. You guys went.
Everyone.
Anyway, we can touch on the result. Yeah, we'll talk about the paper. Yes, let me just show you. It's gonna be segmentation. Yeah, it's gonna be looking exactly like worksheets.
Yeah, by your. Yeah.
1, 2, 3. I'm sure you want to take it after you come back. Feels
Yeah, I guess
rushed.
the coach didn't want it, but the players think.
I'll tell you, let me, hold on,
Just have to be one.
Yeah, like, I can probably learn this shit out. Okay. This is the review worksheets for 1 and 2. I did not attach the key, but worksheet 3 has the key attached. Yeah. Okay. Let me just show you one thing here. When you're doing table of values and I ask you for Riemann sums, it's a little bit different.
Yeah.
It says give middle approximation. So 0 to 20, you want to separate these order pairs into 3 subintervals.
Yeah, you guys can.
So start from the middle.
We have pretty much.
And just make sure that every subinterval scans across the same number of order pairs. They'll all may be different widths, but they all have the same order.
You guys still good.
And then middle approximation, which is width times height.
Yeah.
Okay. Your width is always going to be subtracting your endpoints together. So that's a width of 8. This is a width of 4. And this is a width of 8 as well.
Yeah, so it just looks a little different.
This is a bit different. And then the height, this would be the left height, this would be the right height, and this will be the middle height.
Happy about the Titans.
Yeah. And then so the area or the Riemann sums for this will be 8 times 2 plus 4 times 7 plus 8 times 6. Okay. And then one more thing is we do trapezoids with you. This is at the bottom of. So it says use trapezoids. So trapezoids is 1/2 width height 1 plus height 2, make sure you memorize that. So it says 2 subintervals from 0 to 20. So here, you just have to kind of look to see how you can make it all even. This spans across 4 order pairs. This spans across 4 order pairs. So the width here is 9. The width here is 11. So you got the 2 chopstick formula, but 1/2 times 9, then 4 plus 7, and then 1/2 times 11, 7 plus. What students have issues with here is some students, they want to add up all the heights, but we don't care about the ones in the middle, we just care about the ones at the end.
Yeah. Okay, yeah, that makes sense.
Fine. And then, look through that, and then tomorrow, before you take the quiz, just ask me questions so I can get down to them.
Yeah. Big win.
That's huge one.
Like the Steelers at home.
Yeah, Steelers got in too.
Yeah, playing them just